Hey class, let's go ahead and get started with introduction to learning about aqueous solutions. So it starts with section 1, which is general properties of aqueous solutions. Let's go ahead and get started. What is an aqueous solution? Well, it's a solution in which water is the dissolving medium. In this chapter, we're going to examine chemical reactions that take place within aqueous solutions, and we're actually going to build upon those concepts of stoichiometry that we learned last semester in even the last chapter. So solutions, I've been using this word. Well, a solution is a homogeneous mixture of two or more substances. Remember, homogeneous means it looks the same throughout. So when you look at it, it looks like it just has one phase. Within a solution is made up of two parts. The first part is a solvent and the second part is a solute. A solvent is a substance that's in the greatest quantity and is the one that does the dissolving. Water, you're going to learn, is usually known as the universal solvent because it's able to dissolve a lot of materials since it is a polar molecule. Now, some materials will not dissolve in water, so you have to choose a different solvent, but typically water is the best one. Solute is usually in smaller quantities, and this is the chemical that is being dissolved. So solutes can include things like salt or sugar and other compounds, but those are the most common ones that you know about. A good example of this is when you take a small amount of sodium chloride or salt and you dissolve it in water, you get water as the solvent and sodium chloride is a solute, and the solution is known as a salt solution. So electrolytic properties introduction. At a young age, usually you learn not to take electronics into the bathtub because if you drop them in there, you can have the potential to electrocute yourself. You don't want anything electrical around water. However, pure water, in fact, actually isn't a very good conductor of electricity. And if you actually had pure water and you drop an electronic on it, it wouldn't do anything. So what actually makes bath water and sink water so conductive? Well, bath water and sink water and normal water that you have isn't typically pure. In fact, it has a lot of things dissolved in it. So the conductivity of bath water originates from substances within that water and not really the water itself. Not all substances that dissolve in water does result in a conductive solution. For example, dissolving salt versus table sugar has very different electrical conductivities. Salt is a good conductor, sugar not so much, and we're going to go on to explain why that is. But first, we're going to have to talk about electrolytic properties. On a conductivity meter, and if you've never really seen one, we're actually going to be using one here coming up in a few days. All it is just a little device that has two metal ends. And what you do is you stick those two metal ends in whatever solution you want. And if the bulb lights up, there's a current. That means there's some type of electrical current passing through those two metal parts. If it doesn't light up, it's not conductive. So conductivity occurs because there are ions present in that solution, and those ions carry a positive, if you're a cation, or negative, if you're an anion, electrical charge. This brings us to two vocab words, electrolyte and non-electrolyte. An electrolyte is a substance whose aqueous solutions carry ions. So for example, NaCl can split into sodium ions and chlorine ions. So sodium has a positive, chlorine has a negative. A non-electrolyte, on the other hand, does not form any kind of ions like sugar. And that is because sugar, we're going to learn, is a molecular compound, and molecular compounds are not made up of ions. So let's talk a little bit about dissociation. When an ionic substance dissolves in water, the reason it is split apart is because the solvent, typically water, pulls those ions away from each other, and the water molecules surround it so that the two ions aren't able to join back up. When they surround them, they're said to be solvated. This process is called dissociation because they're splitting apart. They're dissociating from one another. And again, like I've already previously stated, they're said to be solvated. So NaCl consists of Na and Cl minus ions. When NaCl dissolves in water, each of them separate. The ionic solid dissociates into, like we've already talked about, Na plus and Cl minus. Water, we know, is a solvent, and what happens is that water surrounds it where the oxygen, which has a partial negative charge, is going to be attracted to the negative charged anions, and the hydrogen on water, which is partially positive charge, is going to be attracted to the, let's rephrase that. Oxygen, which is partially negative, are going to be attracted to positive ions. Hydrogen, which is partially positive, are going to be attracted to negative ions. So another way to rephrase that is the cations are attracted to the negative end of H2O, and the anions are attracted to that positive end. As ionic compounds dissolve, the ions become surrounded by these water molecules, and they're solvated. And so when we like to write chemical equations, we like to write them as Na plus with aqueous, Aq to show that it's solvated and it's dissolved in water. We have Cl minus to show that it's solvated and split apart and it's dissolved in water. So solvation, the whole purpose of it is it stabilizes those ions and prevent them from recombining. Now we can often predict what ions are going to form whenever we put them in water to be dissolved, just by looking at what makes up that compound. A good example of this is sodium sulfate. Sodium sulfate can dissolve into sodium and sulfate ions. This is going to bring back chemistry a little bit when we learned how to name things. In order to figure out sodium, you uncross these charges. So when you uncross it, this 2 should go up here. Well, honestly, there's nothing down, this 4 can't go up there because sulfate has to have that 4 down there. It was already originally there. So you only have sodium plus 1 and sulfate, which is SO4 2 minus. A good another way to remember this is sodium is in group 1A, so it only has a plus 1 charge. And if you look on your polyatomic chart that you can find either on the internet, sulfate is always going to be SO4 2 minus. So down here, what dissolved ions are present of the following compound? So I want you to try to do these on your own and see what you get, and then check to see if you're correct. So over here, potassium, Cn. Potassium belongs in group 1A, so it is always a plus 1 charge. Cn is a polyatomic. So if you ever look on a polyatomic chart, Cn is a negative. NaClO4, if you look at this, Na belongs in group 1A, so it's always going to be a plus 1 charge. Since it's a plus 1, that means ClO4 also must be a plus 1 since there's nothing down here. You can also check your polyatomic chart, so ClO4 minus. Molecular compounds in water. So when a molecular compound dissolves in water, the solution usually consists of intact molecules. Remember, molecular compounds aren't made up of ions, so they don't really have any charges. They can't produce any kind of electrical current, so most molecular compounds are non-electrolytes. There are only a few molecular compounds that do contain ions, and those are typically acids. So acids are the exemption. For example, hydrochloric acid, which is HCl, when you put that in water, it's going to ionize and dissolve into H plus and Cl minus. Okay. So how do I know once it's electrolyte if it's a strong or weak electrolyte? Because there are going to be varying degrees of strength. Well, electrolytes, again, differ in the extent which they are able to conduct electricity. Some do it better and some do it not so well. So strong electrolytes are solutes that exist in solution completely or nearly completely as ions. They're extremely separated. Water-soluble ionic compounds are usually strong electrolytes, and some few molecular compounds are as well. Weak electrolytes, the solutes, exist in solution mostly in their normal form, and only actually a small amount of them get solvated. So things like acetic acid, most of them are present as acetic acid molecules, and only a few of them separate into H plus ions and CH3COO negative ions. So I like to put this little chart up here, and you guys will see it again. It's just a summary of how to tell if something is a strong, weak, or non-electrolyte. Ionic compounds, all of them are strong, and neither of them are weak or non. Where you're going to run into trouble is molecular, whether it's an acid or a base, and strong acids versus strong bases. So let's break this down even further. Strong electrolytes are strong acids, strong bases, and any ionic compound. So what is a strong acid and what is a strong base? There is actually only 7 strong acids, and they are listed in the table below. Hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, nitric, and sulfuric acid. If you see any of these, it's automatically a strong electrolyte. Strong bases are anything in group 1 metals that combine with a hydroxide. So they are listed as follows. Or any heavy group 2A metals. So heavy means they got some mass to them, so they're farther down in their group. Things like calcium, strontium, and barium. Now, I've been mentioning electrolytes and them being solvated. Don't confuse their solubility level with electrolyte strength. Those are 2 different characteristics. Those are 2 different properties. For example, acetic acid is actually really, really soluble, but it's a weak electrolyte. Whereas calcium hydroxide is not very soluble, but the amount that does dissolve dissociates almost completely to make that strong electrolyte. So how do we identify them? This is your most important slide, if I had to say anything, because this is the slide that's going to help you with your homework the most, because there is a systematic questions that you can ask yourself to get to the answer. So if you remember the common strong acids and bases, and also remember that NH3 is a weak base, we can make reasonable predictions about electrolytic strength of water-soluble molecules. So again, you have to know if something's an acid or a base. Now remember, most bases have hydroxide in them, and most acids begin with H. So let's go through the following questions you would have to ask yourself. The first question you ask yourself is the substance ionic or molecular? So that's what you ask yourself. Remember, ionic is between 1 metal and 1 non-metal. If it's ionic, it's a strong electrolyte. Molecular is 2 non-metals. You could say or metalloid. If you say it's a molecular, you go on to question 2. So if molecular, we have to ask whether something's an acid or a base. So you know if it's an acid if it begins with H, and you know it's a base if it begins with OH. The exception is anything that is an alcohol. Alcohols end in OH, and their name ends in ol. Name ends in ol. These little stinkers are always going to be non-electrolytes. Okay. So if it is an acid or a base, you have to go on to question 3. If it is not, we can say that it's a non-electrolyte. So question 3. If it's an acid or a base, is it a strong acid or base? So you would have to refer back to that table. If it's a strong acid, it's a strong electrolyte. If it's a weak acid or base, it's a weak electrolyte. So let's kind of go through these examples. First, I want you to try them on your own and then see how well you do. So take the time to try them now. Okay, so let's see how you do. 1, it says classify the following as either strong, weak, or non-electrolyte. So the first question, if we go back to our questions, we have to ask if it's ionic or molecular. So we know that calcium is a metal, chlorine is a nonmetal. Metal and nonmetal means that it is ionic, which means that it is a strong electrolyte. HNO3. So we have to look if it's an ionic or molecular. Well, hydrogen is a nonmetal. Nitrogen is a nonmetal. Oxygen is a nonmetal. So we know that is molecular. So we have to go on to question 2. Is it an acid or a base? So we have to see if it starts with H or ends in OH. Okay. Well, it starts with H, which means that it is an acid. That takes us to question 3. Is it a strong acid or a weak acid? Oops. So here, HNO3, we have to refer to our acid table, HNO3. So I go over here, HNO3 is considered a strong acid. So it's a strong acid, which makes it a strong electrolyte. So strong. Okay. CH5OH. Here, carbon is a nonmetal, hydrogen is a nonmetal, oxygen is a nonmetal, and again, H is a nonmetal. Now, I provide the name here. So 1, I know it's molecular. So I know it's not strong. Then I ask myself, is it an acid or a base? Well, it ends in OH, but wait, there's an exception. Alcohols. Does its name end in ol? Ethanol. Well, it does. So if the name ends in ol, it's automatically a non-electrolyte. So you can write it ends in ol, it's a non-electrolyte. Okay. Then we go down here, this example. If we look at all these are all non-metals, which means this is molecular. That takes us over, and we have to ask ourselves, okay, molecular, is it an acid or a base? Well, here I give you the hint that it's formic acid. Also, another hint is it starts with H. So yes, it is an acid. And then we have to ask ourselves, is it a weak or strong acid? So if we go back up to our acid chart, you don't see it under the strong acid, so it's considered weak. So therefore, it is a weak electrolyte. And the last example, KOH. Well, K is a metal. OH is a nonmetal, so that means it's ionic. And therefore, it is going to automatically be a strong electrolyte. So how can you test if a solution has an electrolyte and how strong or how weak? Well, just like we mentioned previously in this, you're going to use a conductivity meter. So the first thing you're going to do is put that substance in water. Then what you're going to do is you're going to connect a battery, and you have a light bulb, which is your conductivity meter. You're going to put the wires of that conductivity meter into that water solution. If the bulb lights up, it's an electrolyte. And the brighter the bulb, the stronger the electrolyte is. So that's the end of today's lesson. Let me know if you have any questions, and I hope you guys have a good day.